Okay, we will begin with this equation, this one, and we'll further analyze it. Mu to the power epsilon, this factor is a common factor, so it goes away. Then epsilon is an arbitrary parameter which is tunable, and we should just collect terms of each power of epsilon and set them to 0. That is basically what we are going to do. So so let me write this equation down there on this other side. Where this is given by so this gives epsilon lambda plus epsilon multiplying k equals 1 term here, gives you a1 plus for other values of k, for the contribution coming from these terms, for other values of k will be written at the end. Let me write the second part. So beta, then epsilon beta 1 then epsilon beta 1 multiplying this term for k equals 1, which is beta 1 a1 prime. So these are the terms which are positive or 0 power of epsilon, and all the other terms have negative powers, and they are k equals 1 to infinity 1 over epsilon to the power k. From here, since there is a epsilon factor outside, it will be a k plus 1 plus beta a k prime, that is this multiplying this term, and the next one is beta 1 a k plus 1 prime equals 0. So equate coefficient of each power of epsilon on both sides. So epsilon to the power 1 terms, there are 2 terms like that. So that is beta 1 equals minus lambda. That's order epsilon. Then order epsilon 0 will be given by these 3 terms. And so this is order epsilon, and then beta equals minus a1 minus beta 1 a1 prime. Beta 1 is, by the previous equation, is minus lambda. So this is plus lambda A1 prime. So this is so minus, one can write it as minus 1 minus lambda dd lambda acting on A1. This is epsilon to the power 0 term. And then epsilon to the power minus k term is this one, which is ak plus 1 plus beta ak prime plus beta 1 ak plus 1 prime equals 0. This is epsilon to the power minus k. And this can be written as 1 minus lambda dd lambda of ak plus 1 equals ak prime times beta, where beta is, so this is minus ak prime times beta on the right hand side, but minus beta is, according to this equation, is 1 minus lambda dd lambda acting on A1. So that is 1 minus lambda dd lambda acting on A1. So these are the three equations that we get. So if we have, so first of all, if we know what A1 is, A1 has a lambda expansion, of course. If we know what A1 is, beta is given by, beta is defined to be mu d lambda d mu. So this is the expression for mu d lambda d mu, and A1 is a function of lambda, which is a lambda expansion that gives you a first order differential equation for lambda, and solving that, one can find lambda as a function of mu, which will that is the running of lambda. Similarly, if one knows lambda A1 as a function of lambda, then one can calculate a, so one can set k equals 1 here, then it's A1 prime. That is also a known function, and then this gives a, so the right hand side is known for k equals 1, and this gives a first order differential equation for A2 if we set k equals 1, and solving that one can get A2. So this is a recursive relation which can be used to find higher residues. By knowing the lowest residue, you can get the higher residues by using this equation without doing explicit Feynman diagram calculations. That's the usefulness of this equation. But now let's, for the moment, focus on this equation where this is given by mu d lambda d mu, and find the running of the coupling. So explicit computation of counter term performed earlier gives you mu d lambda d mu to be equal to the result that I have written down here. Is this is going to give this, the result is this we use this expression here. So minus 1 minus lambda dd lambda of a1, where a1 has been calculated up to lambda square as 3 lambda square by 16 pi square. So 3 lambda square over 16 pi square plus order lambda cube. So that gives you minus 3 lambda square by 16 pi square plus lambda dd lambda, just it counts the power of lambda. So this is 2 times 3 lambda square by 16 pi square plus order lambda cube. So that is given by, so that it just flips the sign. So 3 lambda square by 16 pi square. So neglecting order lambda cube terms, one finds the differential equation to be, so d lambda lambda to the minus 2 is equal to 3 by 16 pi squared times d mu times mu to the minus 1. Now we just integrate it. Then we get minus 1 over lambda minus 1 over lambda bar equals 3 by 16 pi square of log mu divided by mu bar. So lambda corresponds to mu and lambda bar corresponds to mu bar. And the same equation can be rewritten as lambda minus lambda bar is equal to 3 over 16 pi square lambda lambda bar log mu by mu bar. Which is same as lambda times 1 minus 3 by 16 pi square lambda bar log mu by mu bar equals to lambda bar. In other words, lambda of mu is equal to lambda bar 1 minus 3 over, okay, let me write it this way, lambda bar divided by 1 minus 3 by 16 pi square. Times log mu over mu bar. So what one sees is that if you start with a coupling lambda bar at scale mu bar, then if you increase the scale mu greater than mu bar, lambda mu will be less than lambda bar. So lambda mu increases with mu, and as a result, so the result is that lambda mu increases with mu, and therefore the perturbation theory is more accurate at lower energy or larger distance, because at higher energies lambda becomes stronger. perturbation theory more accurate at lower energy or larger distance. So at the infrared, more in the infrared, the perturbation theory is better defined. And this goes very well with the calculation of scattering amplitudes, because in the scattering amplitude you start out with initial states where the particles are far apart, and that's where the lambda is 0, because when the particles are far away from each other, the interaction is negligible or 0. But as the particles come closer to each other, they smash together, then lambda gradually increases. And if the energy with which they are smashed together is higher, that is, the scale mu will be higher, then the particles will explore shorter distances where lambda will be higher, and those results. So at higher energy, the perturbation theory becomes more and more unreliable. Not only that, you have a specific value of mu where the coupling diverges, because there is a value of mu by mu bar such that this denominator vanishes. So that value is given by, so coupling diverges at a finite scale, which is given by mu equals mu bar e to the power 16 pi square over 3 lambda bar. So that mu by mu bar is given by e to the power 16 pi square by 3 lambda bar. So that logarithm of that is 16 pi square by 3 lambda bar, and 16 pi square by 3 lambda bar multiplying this is giving you 1, and therefore 0. So that happens at a finite scale, and it is usually called Landau point. However, when the coupling increases, the perturbation theory, before reaching the Landau point, much before reaching the Landau point, the perturbation theory will become unreliable, and we will not be, it will not be legitimate to keep only the leading order approximation to this differential equation. This is what we did. We neglected this order lambda cube term. So when you increase the scale and lambda becomes large enough so that you cannot neglect it, this term also becomes reasonably large with respect to this, then you cannot neglect it, and therefore the differential equation changes. But so one has to find higher orders in lambda terms and to make more accurate prediction for the running, and without that one cannot rely on this result that the coupling diverges at that point. So, however, the original equation for lambda mu becomes invalid much before this point is reached. And therefore, the conclusion is unreliable. Having said that, it is still a possibility that after incorporating higher order contributions, it is found that the coupling grows monotonically and the perturbation theory breaks down at some point. It's just that we cannot make a definite statement. It is regarding that. It is otherwise, in principle, a possibility. So having said that, it is still a possibility that after incorporating higher order contributions or even non-perturbative calculations, it is found the coupling grows monotonically and the perturbation theory breaks down at some point. Before going further on this, let me just make a comment on this, that if you had considered on a different scenario, if we had considered minus lambda by factorial phi-fourth theory instead of lambda phi-fourth theory, then because of the flipped theory, because then for the flipped theory, this sign will be this sign will flip because the differential equation has on the right hand side the sign flips. This sign changes. This sign changes. I mean, this is lambda squared. So under lambda going to minus lambda, this remains the same, but the left hand side changes, which is linear in lambda. Then you can just simply conclude it from this. So here also you can flip all signs of all the lambdas. So lambda bar becomes minus lambda bar, this becomes minus lambda, and this becomes plus, and then you have the same equation with this as the plus sign. So in that case, what it would mean is that with increasing scale, lambda is lowering, becoming weaker. So the coupling reduces and the perturbation theory gets better at higher energies. In fact, the theory becomes completely free as mu goes to infinity. So I have already explained that. So let me just directly write down the result. Of course, this theory has quantum instability, non-perturbative quantum instability because of the wrong sign, just like in phi-cube theory. But that is not visible in perturbation theory. This is not visible in perturbation theory. Now, this situation where the coupling reduces, so the coupling reduces at higher energies. Or lower lengths, and theory becomes free as mu goes to infinity. And such a situation, such an effect is called asymptotic freedom. And the theory of quantum chromodynamics, where the quarks, which describes the quarks and gluons, which is non-abelian gauge theory, and fermions coupled with non-abelian gauge interactions, there it indeed happens, asymptotic freedom, and which is why the quarks are confined, because it only means that at very high energy, at a very large, at a very small length scales, the particles are behave freely. They don't interact with each other strongly. But as they are taken away, or they are separated more and more, you try to separate them, they use more force to confine, because the coupling increases as you try to increase the length scale of the object. So it is not a proof, but this is an indication that this kind of sign for the beta function leads to something. That is what is happening in the, we observe that in nature, and the sign of the beta function calculated for that theory is consistent, which is the case here in this toy model, is consistent with that observation. Okay, so we shall further study the beta function and the various scenarios of that in next lecture.